two major sorting algorithms. One, the insertion sort. The other one is called as the merge sort. And before that, of course, we will start with the problem statement and also give some terminologies of the sorting in general. Okay, because first of all, we should define the problem. What is the input? What is the output expected, etc. Because for any algorithm in this course, my sincere advice to you all to make sure and don't forget this. Okay, make sure that for each algorithm, what is the input and what is the expected output. If you're clear about this, then I think the rest will go on. And the other important aspect which you should keep in mind is the study plan as far as this course is concerned. What is the meaning of study plan? The study plan includes point number 1, statement of the problem. The problem statement, in other words. So you should understand what is the problem which we're trying to solve. Point number 2 is the strategy or the method. How are we going to solve? What kind of methodology which you are going to apply? Now, as I said in my first session, we have several methodologies: brute force, divide and conquer, decrease and conquer, and queer, backtracking, branch and bound. So many methodologies. So which one you are going to follow? The third one is an example or a sample data set, and apply this method and show how it works. The step-by-step one, that is walkthrough. The fourth one is the algorithm, right? The algorithm is, once you know the strategy or the sequence of steps, then you can easily formulate the algorithm. Point number 5 is the analysis, complexity analysis in terms of big O. So implementation coding, that is not part of this our course, so we will not worry about that. So these 5 sequence of steps in the same order, you should make sure for each and every problem. It could be sorting problem, it could be searching problem, it could be networking or graph problem, anything. You should have these 5 in mind. So that's exactly what we are going to do today, even for this problem statement. Of course, it's general because it's sorting. Method, there are 2 methods, insertion and merge sort. As far as this current session is concerned, we will add some more methods in the upcoming sessions. Then example, I'll be showing some examples for this, and algorithm and analysis. So all these 5 steps will be included in this discussion. So what is the problem? What exactly we mean by sorting? Sorting is nothing but ascending or descending given a set of elements where in an array. So you may be given 1 to n or 0 to n minus 1. What is the name of the array? A is the input array. So what is that you are supposed to do it? Order this in ascending or descending. How you are going to do it? It's left to you. You may follow bubble sort, you may follow quick sort, you may follow insertion sort, anything. But ultimately, I want my ordered element either ascending or descending in A. By default, we'll assume ascending. Okay. So there are 2 types of sorting in terms of the stability. There is stable and unstable. The stable algorithm simply means that supposing if you get duplicates in the array A, then whatever the positions which it was there in the original input array, it should be there in the output array also, sorted one. If the algorithm maintains that, it is called as stable. Algorithms which do not follow this, they are called as unstable. So which are the algorithms which follow this? Bubble sort, insertion sort, merge sort. In fact, we are going to talk these two. That means it will do it in such a way that even if I have duplicates in my input array, whatever it was there, for example, if two duplicates are have been there in A as fifth location and say 10th location, fifth and 10th locations, then after sorting, it should follow the same order. You should not interchange because after all it is duplicate. So I can put that first. The second one which was there in A, I can put it first, and which was there in first, I can put it in second. After all it is. No, you should follow the same order. Unstable one which do not follow this. So quicksort, heap sort, they don't follow. Another interesting terminology used here, definition, is known as in-place sorting. So what is in-place sorting? If the elements after sorting resides in same A, that means you keep the input array in A itself and try to move the elements, compare and move, such that finally, after a few iterations, if it is sorted, then in the sorted one is there in A itself, it is called as in place. Supposing if it's not, if the sorted one is somewhere else, then it's called as non-in-place algorithms, not an in-place algorithm. For example, bubble sort, insertion sort, all these, they actually, even quicksort will keep in the same, use the same array and for the input as well as the output, but merge sort actually it is not. So what we do is we use an auxiliary array and from there you will copy back into A. So that's not in place. Looking at the complexity of the various algorithms, you can see here bubble sort n square because two for loops will be there. I hope that all of you would have already studied this because the bubbling concept, so adjacent elements are compared and it is actually swapped. And at the end of the first iteration, the largest element will be kept at the last position, assuming ascending order. And the next iteration will concentrate only on n-1 elements. Best case, the input, inner for loop, if it is not executed at all because the input elements are in such a way that they are already sorted, then probably there is no need for double for loop. One single for loop will complete the job. So that's why it's called on of the order of n. That is the best case. But this may not happen always. Okay. Next, selection sort. Selection sort again, all cases n square, insertions same, merge sort also n log n. So n log n is better than n square. And quicksort only there is a difference. Worst case is n square. We will all study this why it is like this, n square. And average and best case is n log n and etc. These are all comparison based sorting. These are not. So let's now start with insertion sort, for which the real world analogy is called as the Indian rummy. I hope that most of you would have already played this Indian rummy, where you have different shapes, club, spade, odds, all that. And 4 players, 12 cards each, I think. 12 or 15, okay. So the idea is to make sure that you make the ordering either 3 or 4 cards for each shape and etc. etc. So what we need to concentrate in this example is only this. Now, that's where the insertion sort concept comes into picture. Now, in this particular game, for each player, you would have seen that the cards are initially shuffled and then distributed. And the cards will be lying on the floor, right? It will be lying on the floor. So there's one card, second, third, fourth, all that. Now what happens? Each card is picked one at a time and it's kept in the hand. And the second card is picked, and when you try to, bring it to your hand, you will make sure that it matches with the shape and also the order. So assume a scenario like this where one of the players has already picked 4 cards and this is the 5th one. OK, this is the 5th one. So this is the key. I can call this as the key. Now you can see here the cards which are already there in the hand are sorted 2, 4, 5, 10. So this is called as partially sorted. Now the new card has to be put or inserted in such a way that it's going to maintain this ordering, right? So what we should do, or what the user is supposed to do, he should make sure that this card is inserted by comparing with the existing cards in the hand, which is already sorted, such that after inserting it should be in order, for which the user might compare from right to left or left to right. So let's say right to left. So starting from here, 10, it's less, so he will go and make room for this to insert. That's exactly what we are going to do or follow in this insertion sort mechanism. So this is the strategy. We have understood the problem statement. Now we have understood the method or the strategy, how we are going to sort it. Take the next card. Let's assume that the next card is 3. OK, now it will be compared with 10 less, compared with 7 less, compared with 5 less, compared with 4 less, and compared with 2 because it's not less, it will be inserted here. So like this, each and every card will be taken one at a time and then it will be inserted. That's exactly what even players will be following. So to follow this, let me just show you a simple 50-second or 30-second video. OK, so now you can see here shuffled. OK, there's a card being picked. So now he's making it sorted 1. Queen is bigger than 10 and he keeps inserting. See, 7 is less than 10. OK, now again 9 is inserting. Now it's the smallest one, so it goes into the first position. And similarly, Jack is less than Queen, so it's in the ascending order, J, Q, K, A. And now it is 5, 6, 7, 8. And 2, 3, 5, 6, and 2, 3. So that's done. OK, so this is exactly the strategy which we will follow here by picking up a sample data, right? OK, so this is my partially sorted array. So what I'm going to do here, I'm going to walk through this example in order to make you understand how the insertion sort works. So we have around 9 elements are there. And the first element need not be sorted because it's in the current position. So we'll start from the second, right? If we start from 0, then it is from 1. Okay, so 26 is the key or K, which will be compared starting from the previous element onwards up to 0th location, because you should not go beyond this. Okay, should not go beyond this. Okay, now 26 is the key and it's compared with 54. So now 26 should be inserted prior to 54. See, we don't have space here, right? So for which we should actually move this to the right so that you can make space for that. So whenever you try to initiate this iteration, any iteration, you should make sure that starting from here, you can save this in terms temporary one like K, and make sure that if it is less than the previous element or the prior element, then you can move this to its position. So that's what done. 54 has come here. 26 is inserted here because we already reached the 0th location. Next one is 93. 93 is compared with 54, which is already greater. So no need to move. Next one is 17. So that's why you can see it's retained. Next one is 17. 17 is compared. It's less. So move this here. Right? And 17 is less than 54. So move this here. You can see here. And 17 is less than 26. So move this here. 26 has come here. And since we already reached the 0th location, stop there and insert this key, which is 17. You can see. Now the shaded portion, remember, this is all partially sorted. OK, this is all partially sorted. Whereas the non-shaded portion are to be sorted. That's where it is equivalent to these are the cards which are in the hand. These are the cards which are lying on the floor. So next take 77. 77 is less than 93, but not less than 54. So this is the place where this has to be. So 93 would have already moved here. So I can easily insert 77. So the next one is 31. Same thing, less, but not this. So it has to come here. So you can see a 31 has come. Next one is 44, less, but not here. So it should come here. Because 93 would have gone here, 77, 54. So you got a place for 44. Next one is 55. Same thing. Less, but not this. So 77, 93 have been pushed and 55 has been formed this place. Next one is 20. Less, except this. So it would have come here. So in the process, all these things would have been moved by one location to the right, and you got the position for 20. Now you can see that 17, 20, 26, 31, 44, 54, 55, 77, 93. It is in the order, ascending order. So insertion sort means that we maintain in the same array A. Okay, both. That's why it is in place sorting methodology where you have all this shaded one partially sorted, non-shaded one is not sorted, and we pick keys like this one by one and try to find a place to insert. In the process, you should keep moving the elements towards the right. So this is the strategy which has been obtained from cards, especially the game Rummy. And now we have to formulate the algorithm. So how do we formulate? We have so many iterations. How many iterations? N-1 elements. Correct? Why? Because the first element, no need for comparison. So we need to start from here and go up to this, which is n minus 1. So 1, assuming 0th location is the starting one. So the outer for loop will be from 1 to n minus 1. Each element is taken and compared. This also requires, because with one iteration, once you any level, it's not going to end, because for example 20 you take. In this iteration, I have to compare with all these elements. Almost n minus 1 elements I would come. So the worst case, this also may require these many iterations, but we don't know. Some cases it may require 1, some cases it may be 2, some cases it may be 3, right? So we do not know. So we need a while loop for that, because while loop is not a definite loop. This one is a definite loop, so we can go for a for loop. For I equal to 1 to n minus 1. Use a pointer in order to track this, picking each element. Once you picked up an element, then you can establish the while loop in order to compare and decide which position. So all these things now will appear in the algorithm. So the input parameters, array A is 0 to n minus 1 and n is my size, and sorted array will be there in the output. So the input is given array unsorted, and the sorted array also will be there in A. So this is what I said, the outer for loop for I equal to 1 to n minus 1. Do. The the inner for loop, while loop is going to iterate depending upon some conditions, obviously, because we don't know where it's going to find its position. So first pick the key pointed by J. So you have this, right? So for example, this may be 5 and 7. Right? So J pointer will move from here. As I've already told you, first one is not required. So the next one may be 6. So move from here to here. So this J will go from 1 to n minus 1 as now pick the key pointed by J, which is 7. And I will be J minus. So there is I pointer. Which will actually go through the entire iteration depending upon, for example, it may be somewhere here. So it has to move from here to here. Right? So let's assume some more elements. Maybe this is 16. This is 60. Let's assume that I have 8. So this is partially sorted. And this is partially sorted. This is the element to be sorted, key element. Because now the pointer will be different. OK, so now I have my what? Key element. That is J is the pointer and key element is 8. Right? K is 8. Now I is J by, because I have to start comparing from right to left. OK. So I will be here. Now I'm going to move this I pointer from this position up to this, not below, beyond this. That means as long as I is greater than or equal to 0. That's my first condition. What is the second condition? I can't keep on moving this because I can only move only when the elemental value pointed by j is less than this. So that means the key is less than pointed by a of I. So as long as k is less than a of I can keep this decrementing, you can see here. But while decrementing, I should also make sure that these elements are pushed towards the right. Right means I plus 1, you know. So current element will take or will be pushed to the next element. So for example, 60 will go here. 16 will go here. That's all. So I get a room here. So when I comes here, I know that it is no longer less because 8 is greater than 7. So I stop. And I plus 1th position, I can put this. So that's why I plus 1th position, I can put my element pointed by, key element, I can push it or insert it. So inside this loop, I should do two works. One, pushing the elements towards the right. The next one, keep moving my pointer I by 1 towards the left. So next point is, when does this loop break? Either the element is so small until you reach 0 or in between. So this is in between condition. This is smallest one. But we don't know because of which. In any case, no problem. No need to check because it will be stopped, you know, that particular kth position. I'm sorry, the ith position. I'm going to stop anyway. And I can insert the element, as I said already, I plus 1th position. Now, once if I finish this one iteration for pushing the element, then I can go to the next element being picked from the unsorted array, subarray. Same thing like rummy cards. Now at this point, so you can practice some more exercises and come out with some. So how do we analyze? As I already pointed out that you have two loops here. One is the outer for loop j1 to n minus 1 and the inner one is from 0 to j minus 1. I think if you look at the algorithm, you will notice that the inner loop goes with 0 to j min. Now the effort being put is 1 unit of time. And we have formula. I think this is the place. In fact, if you recall my first session, I've told you that summation formula, there is a chart. So we have 8 formula, which I have mentioned here in this slide. And if you go through my book, you also get this information. So you can see here upper minus lower plus 1 when the effort is 1, that is 1 plus 1 plus, there is a summation. Similarly, if it is 1 to n, example, upper minus lower plus 1, n minus 1 plus 1, which is n. Upper 1 to n minus 1, this is n minus 1, n minus 1 minus 1 plus 1, so n minus 1. Supposing if you have n, that is 1 to n only for all the cases, that means n plus n like that. So you can see here it is n square. OK, up because n you have to take it out. Okay, I'll just show it here. N you take it out, then I equal to 1 to n, then 1. So this n minus 1 plus 1 is n. So n into n is n squared. So 1 plus 2 plus this is natural number summation. This you have already studied in your schools, n into n plus 1 by 2. So it's of the order of n. And there is a proof for this also. I leave it to you. So similarly, we have so many formula which we'll be using later in our discussion. So in our case here, so it is j minus 1 plus 0, that plus 1 plus 0 minus 1, sorry. sorry, not -1, +1. So j -1, upper minus lower +1. So j. So that's what is written here. So this summation 1 to n minus. So j means we have a formula like here. Instead of I, we have a j here. So it is n into n minus 1. Because this is up to n minus 1. Remember, it is up to n minus, you can see here, f3. So f3 is used here. This is n into n minus 1 by 2. So that's the formula. F3 is used. Use f3. So what is this? F of n. So what is the big O of n? N square. Dominating factor, that's all. So the worst case time complexity of insertion sort is n square. What is the best case? As I said, in inner while loop, if it's already sorted, let's take, if the list is already sorted, inner for loop will never iterate through. So only outer. So outer means it's very simple. N of the order of n. So best case is n. What is the average case? What is the meaning of average case? So your, this element key, sometimes it may get a place here for insertion. Sometimes you may have to go all the way through this, get a position. So then when I take ith element, there is an equal probability of it to be inserted at any of these positions. So it may be here or here. So there's an equal probability. So we have to calculate the probability for its insertion depending upon the value of the element and then divide by those many elements. OK, which means taking the average case. So add up all these possibilities and divide by this. So we'll get the average. So that's exactly what we are going to do for the average case. So you can see here, this is the effort being put in the loop for the comparison purpose and take the summation from j equal to 1 to I minus 1, that's the inner one, and divide by this. Then we'll come to the outer for loop. The outer for loop, there is no problem. Actually, there is no probability. Anyway, you have to go through n minus 1 iterations. So that's exactly what is shown here. The problem is only for the inner for loop, inner while loop, sorry, where we have to take the average. So we are trying to take the equal probability of the I being placed everywhere, any of the places, and take the average. So if you look at this, it's also n square. Very simple. So the worst case, sorry, the average case complexity is n square. Now we'll move on to the next algorithm called as merge sort. So what is merge sort and what are the prerequisite topics we require in order to understand the merge sort algorithm? The prerequisite topic is divide and conquer, which is one of the very important and famous problem solving technique. DNC means divide and conquer, just like our Britishers those days. They adopted this method in order to conquer India and not only India, maybe other countries also, such that they have finally conquered. They divided and then conquered. This is applicable even for this, example of merge sort. Now, what exactly is the meaning of divide and conquer? It's very simple. So when you look at the problem size, sometimes it is so big. Assume that n is very big. Now, our aim is to sort. Let's take n is 1 million. 1 million elements. Now, how do you attack this problem? It's not so easy. No? Okay. Now n is two numbers, only two elements. Say for example, 11 and 2. So sorting these two elements is very, very simple. So when n is so large, it's not so easy. But when n is very small, I'm able to do this. So what we are going to do is this n, which is so big. Now I'm going to divide this into two halves. That is n by 2 and n by 2. Next, I'll divide this further into two halves. That is n by 4. Right? This is n by 4 and n by 4. And this side again the same thing. I'll divide this into two halves, n by 2 and n by 2. Next again, this I will divide into 2 as n by 8. Divide by 2 again, n by 8. Same thing, n by 8, n by 8, n by 8. And keep going until my size becomes so small, maybe 2 or 1. So instead of solving the problem whose size is so big, I can solve when the problem size becomes small. That is divide and conquer. Many problems, even today, if you look at the research papers, some of the complex problems have been solved by following this strategy. In fact, one of the very famous papers is image processing technique or image analysis technique, for which this divide and conquer, if you use, then it's going to speed up the entire process. Right. Because algorithms, if at all they execute faster, then only people will appreciate, especially when the data is multimedia or media in general, like videos, video, audio, etc. So there are a lot of tools which are very famous, especially the editing tools, video editing tools, like iMovie, right? Or Adobe Express, Photoshop, Clipchamp, I think I already told you. So there are very good number of very famous algorithms. All these things are very efficient algorithms in terms of time. Otherwise, you can't edit these things. And it's a billion-dollar industry again, because nowadays everything is digital and people are desperately looking for these kinds of editing tools. Okay, so now this divide and conquer, we'll just take P and R as the original size, because we'll operate only through positions rather than the actual number of elements. So if it is very small, as I told you, that you can decide, because it varies from problem to, it changes from problem to problem. Because in my case, if it is 1, then you can say up to 1, that is P and R, or P less than R. So the problem will be solved. If that condition is not true, that means you have more elements. So when the problem size is so small, you can return the answer. Otherwise, you find the mid, as I said, and attack the problem left half. This is left half. So P to Q. Q, assume that this is the mid. P to Q, Q plus 1 to R. So 2 halves. But you are sending this to the what? P, new value, the left subtree, and this is the right subtree. So what is the ending point? Is a Q for the left subtree and or left sub array, you can call it. And for the right subtree or subarray, R is the ending point. Starting point is Q plus 1. So this keeps recursively going because we are going to do the same work until it becomes small. But there is one very important and challenging work is how to combine these results, because you would have solved when the size is small. But actually, I should be getting my bigger problem solved, not the smaller. So I have to combine all the solutions and then take it back to the problem size, original problem size. So that process will be done by this combine. So we will apply this strategy to our merge sort. This is also called a split merge because the first phase is splitting the array into two halves. Keep going until the size of the array becomes 1, and merge is the second step or second phase. So assume these elements and the starting position P and R, and mid one is Q because 0 plus 7 divided by 2 is 3.5, which is floor. So 0 to 3 is 1. And Q plus 1, that is 4, 2. So this one is the right subarray. So 9, 11, 6, 2, 14, 7, 3, 12. Next, you take this 0 plus 3, that is 3 divided by 2, 1.5, which is 1. So 0 and 1 will be in one array and 2 and 3 in another array. Next, you divide, same thing this side, 9, 11, 6, 2. And this side, 14, 7 will be further divided, each one, no problem. Same thing, 3, 12, 9, 11, 6, 2. So now we have reached a stage where the size has become 1 and stop splitting. That means stop calling the recursion. So now go back and try to merge these things. So we take this as two sorted arrays and then merge it because one element is sorted. So when I merge these two, it becomes 714. This becomes 312. This becomes 911. This becomes 26. So you can see here 714, 312, 911, 26. Done. Now these two are sorted. Now merge this. So what is that called? It's called a simple merge. So I'll quickly show you in the next slide about that. How simple merge works, or with the same slide, I think. So this, when I merge, it should be ordered. How you will order that will be taken care by a simple algorithm. So similarly, you merge this, make sure that it is in the sorting order. So 3, 7, 12, 14, 2, 6, 9, 11, done. Now this is one sorted one. This is another sorted. Merge this to get this final sorted one. Now let me explain how this simple merge works. So we will take the same example and consider this scenario. Okay, this scenario. So I'll maintain 2 pointers. And let me call this as A, array A. This I'll call it as the auxiliary array B. Okay. So I'll maintain 2 pointers, I and J. Remember, we are going to keep all these things in the same array and only the positions will tell us. For example, the starting one for this subarray is this, and there is a mid position. So from here to here, I have to do it. Similarly, mid plus 1 up to this R, the final one, I have to. So pointers when I have, I'm just taking for explaining simple merge, but when you have so many elements in the same array with so many pointers, then I think algorithm will explain that. So concentrate only on how two sorted arrays are merged into a single sorted array. So compare the elements pointed by I and j. Whichever is smaller, push it into the third one. So I may call this as another auxiliary array with a pointer, So now 2 is smaller compared to 3, so 2 gets this. And increment corresponding pointer. So I actually moves here. Now compare again the same thing pointed by I and j. So 3 and 6. In this case, 3 is small. So move 3. Copy 3 here. It's done. And move pointer I here. Now compare again pointed by I and j, 7 and 6. So 6 is smaller. So this is occupied and j moves here. So again I and j, 7 and 9. So 7 is smaller. So I moves and 7 has come. Next, one second. Okay. So now 9 is the smaller one compared to 12. So 9 is pushed. So it goes into this. 9 is already pushed. Now compare 12 and 11. So 11 is smaller. Now it is gone to the third one. This array. And now j pointer has reached the end. So now you have to copy the remaining elements pointed by I. It could happen even for this array, in which case you have to copy this. So it's the reverse, ulta, okay? So now blindly you can copy because it's already sorted. Remember, both the arrays are sorted, subarrays are sorted. So 12 and 14 will come here. Now you have the sorted array in the auxiliary array called B. So this has to be done by keeping this in the same array, okay? So that's exactly what I'm going to tell you. There's another example which you can go through. I'll leave it to you. It is splitting and this is merging. So what we do here is you can follow the same DNC, divide and conquer. This is the input array 0 to n-1. Its positions are low and high. Original, no, I'm not using P and Q, so I'll use that later. But for the inner one, but for this, because there will be a lot of variables being used. So you have the original array with low, high. That's all. Okay, original array with low and high. Right. So this is my low, this is my high. This is my A. So if low is, because it's a recursive algorithm, we should provide an escape kind of thing. If low is less than high means when there is only one element. When you have more elements, of course, you have this concept of it will keep calling recursively. So first, calculate the mid position, that is low plus high by 2. And call this 2 recursive one, as I've already, DC, DC. So low to mid, mid plus 1 to high. So this corresponds to the general algorithm DC starting and mid plus 1 to ending. Now this is a simple merge which I have explained just now. OK, for which I'm supplying all this because it's there in the during every recursive call. I'm sorry, this left and right recursive calls, you have to be very careful because after this only it's going to be merged. Simple merge starts only after this recursive call ends. So this is split. This is merge. This is merge. That is simple merge. So after this recursive calls end, then it, as I already explained with the sample data set, it actually starts the merging process. Fine. Now we have to concentrate on this algorithm, how it works. So this is the merge where I'm supplying all this low, high, mid, and I have my OK. So you have low, mid, high. This is your low. Let's take this as mid. High. OK. So this is my mid. Now I'm going to use two more temporary variables called H and I. And J here, mid plus 1. So this is H. I is for the third auxiliary array. So you can see here B is my auxiliary array. So don't worry about that. Maybe I'll just show it here. So this is my B with I. I equal to low is initialized because 0, that's to get that value, that's all. OK. So now pointers are initialized in this fashion. And you can see here H moves from low to mid. OK. Then mid plus 1 to high. Which one? J. So H moves like this. J moves from here to here. Now we have to compare elements pointed by H and J. You can see here. So whichever is smaller, it is going to be pushed. So this one, whichever is smaller, it will be pushed into this. So if H is small, if this condition is true, that means element pointed by H, that is this one, is pushed, smaller one. Else this one will be pushed. That's all, very simple. So whichever is, so this keeps going and pointers are incremented because of the post increment. So both the pointers, depending upon whichever is smaller or through pushing it, we have to increment. Because B, of course, there's no problem. Whenever the element comes here, it will be keep going. So that's the meaning of this. Okay, this one is your remaining element being copied. As I said, if H is greater than B, that means your left subarray is exhausted first. So copy the rest that is starting from J, from right subarray. Else the reverse. Okay, that's the else class. Up to this, the sorting is over and the sorted elements are in B. Now we have to get into the what is called as the element sorted should be available in A, not in B. B is temporary. Okay, auxiliary array. So it should be copied back. This is the original one, should be copied back. So that's blindly you can do that from low to high and copy it. So that's how the simple merge works. Okay, now any doubts? We'll go for the analysis. So we have to analyze this recursive algorithm. Session 1, I have left it, so you can go through that also, but here we will cover that as well. With respect to one standard example or the general example, then pertaining to merge sort. Okay. So this is very simple one. I want to add enough, the n natural numbers. So how do I add? So it's very simple that if I know the sum of all the previous n-1 numbers, then I can simply add. It is something like 1, 2, 3, okay, or anything, 2, 31, 5. If I have 4 elements, so how do I add? So if I know the sum of these 3 numbers, that is n-1, because n is 4. So if I know the sum of all n-1, so in this case 32, 42. So if I have this, then I can simply add that with 5, so which is 47. But how do I know this value? So again, I need to go for n of n-2. So if I know the value of this 10 plus 2, I can easily do that. That's exactly what we do normally. So if I'm given these numbers 10 to 31, 10 to 31, this is common sense addition, elementary school addition. So 5 plus 31. I'm going to do as it is, okay? Not this unit number, then tens, not like that. So 5 plus 31, 36, 36 plus 2, 38, 30 plus 38 plus 10, 48. Okay, so I am taking this nth element and adding with the previous, adding with the previous, adding with, that's exactly what I'm going to show here with the recursive one. So my problem of adding n natural numbers is more recursive because what operation I'm doing this addition of the current, the nth number is going to be added with the previous. Recursively keep doing this. So I have my n-1. Now replace n with n-1. So I'll get s of n-2. This n is there and n-1. Because of this n, I had to reduce by 1. Because basically this s of n is nothing but s of n-1 plus n. What is n-1? That means I have to just make sure that wherever n is there, replace that with n minus 1. So it becomes n minus 2, n minus 1. That's exactly what I have written here. Similarly, this alpha, so you replace n by n minus 2. So this will become n minus 3, n minus 2. So n minus 3, n minus 2. So the old one, n minus 1 plus 1 remains as it is. Same thing, if I continue this, I can come to ith digit, ith iteration. And keep going up to nth. So this is the final one, s of n minus n, this is s of 0. This one becomes 1. Next one will become 2 and so on. So what is this? This is n of, sum of n natural numbers, which is nothing but n into n plus 1 by 2. So it is not while loop where we normally, or for loop, for I equal to 1 to n. Sum equal to sum plus a of I. I think you would have written that there is elementary sum of non-natural numbers, right, with iterative method, but this one is with the recursive method. So that's exactly what we are going to use here in the case of merge sort. So merge sort, we have two recursive, two recursive calls, t of n by 2, t of n by 2, and a simple merge, which involves only the t of n and some operation. So I'll call that as constant operation, which I call it as d, as long as n value is greater than 2. But otherwise, it is not going to be recursive, but it's only some constant operations. So we have to concentrate more on this. So what is this? This is 2t n by 2. That is this one, and dn. So replace n with n by 2. So wherever n is there, make it n by 2. And so this whole thing is for this recursive call. D of n remains as it is. So 2 of t of n by 2 is what? T of n by 4. 2t n by 4 plus n will be replaced with n by 2. So d of n by 2. So plus dn. So this is nothing but 4t n by 4 plus 2 cancels dn. dn plus dn is 2dn. OK, now this further again by 2. So you get this. So you get this. So it actually grows in this fashion like 2t n by 2, 4t n by 4, 8t n by 8, and so on. And you can see here 2, 4, 8. So it grows in terms of 2 power k, where k equal to 0, 1, 2, like that. And 2, 4, 8, that is denominator, goes again the same way. And d, 1 dn, 2 dn, so k. So k dn, you can see here, plus this grows in 2 power k, as I said. 2 power k, I can assume that n grows in 2 power. So 2 power k may be assumed as n. So that can be replaced with n. So for this first one, t by 2 power k is n by n, so 1, t of 1. So this is n. What is k? K is nothing but log n base 2. So this is, in order to get k from this, I need to just take logarithm on both sides. So you will get k equal to log of n. So k is log n, and d. So now n log n, d is constant actually. So n log n is greater than or bigger than n. So I can just drop this. So this f of n, so g of n is nothing but n log n. That means big O of log n. So Yoskai's time complexity of merge sort is n log n. So you can achieve the same analysis by using tree structure, which I'll leave it to you. It's there in my first PPT also, first session PPT. And you can go for master theorem as well, which we have already covered in session 1. So it will lead to the same result here also.